Hello and welcome to the lectures on state space approach to control system analysis and design. The topic now for discussion in today's lecture and subsequent few lectures is design of controllers based on multi-rate sampling, and in that a specific topic to be covered is obtaining a relationship between system state, multi-rate output samples and the input. So far, we have concentrated upon the study of continuous time systems. The inputs, outputs, and state variables in a continuous time system can undergo continuous variation in time. The picture here shows a system with its input on the left and output on the right. Both the input U and the output Y, these are continuous functions of time. Also, this picture which shows the internal variable X and the state diagram of the state equation x dot equal to ax plus bu, y equal to cx. In this, the ut, the xt, dx by dt and yt, these are all continuous functions of time. Means that they can take values at any instant of time. So these kind of systems have been the subject matter of our study so far. We have studied the mathematical modeling, standard state space representation, controllability, observability, stability, before that solution of state equations, design of controllers, etc. Everything was in the framework of continuous time systems. Now we are going to discrete time systems, and of course not the entire subject of discrete time control systems, but only very specific things which are at the boundary of continuous time system and the discrete time system. So the theory of sample data control systems, you might have come across these terms, and discrete time control systems, digital control systems, this has separately evolved. This is subsequent to the various developments in the continuous time systems area. So parallel to the various like controllability, observability, the solution of state equations, this mathematical modeling, etc., we have parallel developments in the discrete time control systems domain and sample data control systems domain. In these systems, contrary to the continuous time systems, the input to the system can be updated only at discrete instants of time. And similarly, the outputs of the system are detected, observed only at discrete instants of time. In that sense, the sample data control systems or discrete data control systems, they differ from the continuous time systems. So once again, in continuous time systems, the input variables, the output variables, and the state variables are continuous functions of time. They can take values at any instant of time. Whereas in case of sample data control systems or discrete time control systems, the input are applied at specific instants of time called as sampling instants. Outputs are detected again at the specific instants of time called as sampling instant, and states can vary depending upon whether it is a digital system or a continuous system. In digital systems, they will vary only at sampling instants. However, in continuous time systems, they may internally vary as a continuous function of time. This is the depiction. Generally, we have like this. We have the system with the input and output. However, At the input terminals, we have a sampler along with a hold. Generally, a zero order hold is used. Similarly, at the output terminals, we have again a sampler and with a zero order hold. So, and the system states may vary continuously in time. However, when a sample and hold is connected to the system at the input terminals and the output terminals, the governing equations of the system become like this with the zero order hold, meaning that the input in between the sampling instants between kt and k plus 1t. So I think this is written here. Between kt and k plus 1t, the input is treated to be constant and it is treated to be equal to ukt. And in that case, the state equation becomes like this, and the output, of course, we are detecting only at the sampling instance, it becomes like this. Now the systems generally we come across are those in which we do uniform sampling, means the inputs and the outputs, they are sampled uniformly at the rate of 1 by t per second, t being the sampling period. So the input is also sampled at the same rate, output is also sampled at the same rate. And not only that, both the switches, the sampler on the input side as well as on the output side, they are synchronized. They close at the same instant of time, and again after t at the same instant of time, after 2t at the same instant of time, and so on. So this is the generally the system we study in the digital control. Now we obtain a specific situation, a continuous time system. When the sampler is introduced, then it gives rise to those kind of equations which we just now saw, discrete time system equations, which corresponds to sampling at certain rate. And we are first going to derive the mathematical model for the situation when a continuous time system is sampled at a rate 1 by t per second. What will be its description that we are going to obtain? Of course, it was written in one of the previous slides, but we are going to derive. There is a simple derivation. So we know that the solution of a state equation, this state equation, given the initial state xt0 at t equal to t0, is this expression. Xt equal to state transition matrix evaluated for t0 multiplied by the initial state x20 plus this integral. You may recall this we called as the zero input response and this we called as the zero state response. This we obtained in one of the earlier lectures. And here this phi t0 is called as the state transition matrix, and in case of linear time invariant system, it takes this value. Phi t0 becomes e power a t minus t0. And of course, accordingly, phi t tau will be e power a t minus tau. So in this one, if we substitute t equal to kt plus t and t0 as kt. So if this is the time scale and this is the instant kt and this is the next instant k plus 1t, they are separated by the duration t. This is the duration separating them, that is t, capital T. So in this we substitute t equal to kt plus t or k plus 1t and t0 as kt. So this we are treating as t0. So if we do that substitution, we will obtain this one. So xt, this t becomes k plus 1t. So x at k plus 1t equal to this phi t t0, because it is e power a t minus t0, and t0 is kt and t is kt plus t. So t minus t0 will be kt. T minus t0 will be just t. And so e power a t minus t0 with these substitutions will be e power at. And this x t0 is x kt. Now T0 in the integral is kt. On the upper side it is t is k plus 1t, so that is substituted here, and e this phi t tau, t is kt plus t minus tau. So e power a kt plus t minus tau, and then the rest is as it is, b u tau t tau. So this is what we obtain by substitution. Proceeding further, because the input is treated as constant during this interval between kt and k plus 1t, because we are assuming a zero order hold along with the sampler, so we can take that ukt out of the integral, and we can write the expression which was there in the previous page, this expression, by taking this u out. U is u tau is ukt during the interval kt to k plus 1t. So we take it out of the integral, and rest of the terms we write as it is. Further, we make a change of variables in this term. So we substitute kt plus t minus tau as a new variable eta, and so we can see that d eta will be minus d tau, and we will see that if tau is kt, then eta will be t minus tau. If tau is kt, then eta will be t, and eta will be t, and if tau equal to k plus 1t, then eta will be 0. So we can check by this substitution. So the lower limit of integral becomes t, the upper limit of integral becomes 0, and this is now e power a eta, b is at it is, d tau is minus d eta, so that is why this minus sign d eta and ukt were taken out of the integral. So we get this one, and of course we have indicated it like this in the brackets which come here, and this is the state equation for the situation when a continuous time system, as such it is a continuous time system, but when we introduced sampler at the input and output terminals at the interval t, the switch was closing every t second, or the sampling rate is 1 by t, then this is the state equation governing the continuous time system for the sampling rate 1 by t. This is a very important result, and it will be used in our subsequent part of the lecture. Now what we do is that this e power at is denoted as phi t, and this integral is denoted as gamma, and then we get the state equation for the discrete time system corresponding to the continuous time system sampled at the rate 1 by tau as this one, which is also, you will find that sometimes it is written xk plus 1 is phi xk plus gamma uk. Of course, we are, in order that we don't miss anything in the lectures, we are not using this concise notation, but we are using this notation very explicitly. We are writing x, this k plus 1 as x, k plus 1 into t. So we are using this notation to express this. Now this is, as I was telling, this is an important result which we'll be using in the rest of the lecture. So with that one, when we derive the system equations for a continuous time system sampled at the rate 1 by t uniformly for both the input and output. Okay, and this is this. And of course, we are going to use this result, but control systems study based on these equations is a very well evolved subject called as digital control systems or discrete data control systems. So now we come to a situation in which we sample the input side at one rate and the output side at one different rate. So we are introducing samplers with different time periods. Sampling rate on the input side is 1 by t1 per second, and on output side the sampling rate is 1 by t2 per second. And what happens in this situation? And of course t2 and t1 are different, they are unequal. So we are going to develop the equations in such a situations, of course with some restriction on choice of t1 and t2. We will see as we proceed further. So at the beginning, let me just say this, that when we introduce samplers with different sampling rates on the output side and input side, if we remove the restriction of uniform sampling rate, then we find that arbitrary pole placement can be done by the output feedback. These results have been developed in the control theory, and we are going to study these things. So in particular, we will study two types of controllers. One controller is in which the output is sampled at faster rate than the input. The input sampling rate is 1 by t0 and the outputs are sampled at a faster rate 1 by delta, and delta is t0 by n. So we have outputs I equal to 1, 2, etc. We have p outputs. So we are considering the situation that input is sampled at the rate 1 by t0. The sampling period for the input is t0. However, for output 1, it is t1, which is t0 by, it is delta 1. The sampling rate for output 1 is delta 1, which is t0 by n1, and n1 is an integer. So delta 1 is t0 divided by n1. We will see what can be the possible selections for n1 to achieve the complete arbitrary pole assignment. The output 2 is sampled at rate delta 2, which is t0 by n2, and so on. Output p is sampled at the rate t0 by np. So n1, n2, etc. are the sampling rates, and of course they are integer. So in the multi-rate output sampling, the inputs are sampled uniformly at every t0 second. Sampling rate on the input side is uniform, 1 by t0. Sampling rate on the output side is also uniform. Each output is sampled at the same uniform rate given by delta I. Ith output sampled at the rate 1 by delta I. Sampling period is delta I. However, delta I is smaller than t0. And the relationship is this, that delta I is t0 by ni, ni is an integer. So t0 is an integer multiple of delta I. And of course, even though each output is sampled at a uniform rate, the different outputs get sampled at different rates, each satisfying this criteria. There is fast output sampling, which is a special case of multi-rate output sampling, in which all the outputs are sampled at the same rate. Ni is same n for each of the output. So inputs are sampled at the rate 1 by t0 and outputs are sampled at the rate n by t0, that is the fast output sampling. We will study these things, but today we will study the first one, the multi-rate output sampling. The other class of controller is called as periodic output feedback, and here the situation is opposite of that fast output sampling or multi-rate output sampling. Here the output sampling interval is large. Output sampling interval is t0 and inputs are sampled at the period of t0 by n, or the sampling rate is n by t0, whereas here the sampling rate is 1 by t0. Outputs are sampled at the rate of 1 by t0 per second and inputs are sampled faster, n by t0 per second. So the distinguishing thing between the multi-rate output sampling and periodic output feedback is one, that in the multi-rate output sampling rate is larger compared to the input sampling rate. And in the periodic output feedback, the input sampling rate is larger compared to the output sampling rate. There is one more difference that will come, that is the periodic. Actually, the gains through which the control is generated, they are periodic functions of time. This we will understand when we actually discuss the periodic output feedback. As far as today's lesson is concerned, the difference between the multi-rate output sampling and periodic output feedback is that the sampling rates. In the multi-rate output sampling and fast output sampling, the outputs are sampled faster than the inputs, and in the periodic output feedback, inputs are sampled faster than the outputs. This is the distinguishing characteristic in this class of systems. Now, as I told, the topic of study here in this lecture is multi-rate output sampling, multi-rate output feedback based controller, and in this specific lecture we will be deriving a relationship between the system state, the multi-rate output samples, and the inputs to the system. So we start with this, that we have the linear time invariant system, x dot equal to x plus bu, y equal to cx, state equation and output equation. We have n state variables, m is the number of inputs and p is the number of outputs. We are given with this system. Now, as we said, that we are connecting a sampler with the sampling period t0 and 0 under hold at each input. So we have ut constant during the sampling interval between kt0 and k plus 1 t0. It is equal to kt0 because input is sampled and kept constant with a 0 order hold. So this is the input. Now the state will of course vary during this, and as we derived earlier, the variation of state during this interval will be given by this expression. Tau is between kt0 and k plus 1 t0. So let us say this is kt0, this is the next sampling instant k plus 1 t0, and tau is any arbitrary time between these two instants, between this instant and this instant. We are somewhere in between the two and the measure is tau, and it is being measured of course from here. So at any time past kt0 given by kt0 plus tau, the state x will be given by e power a tau into x k t0. This will be treated as, the state here will be treated as the initial state, plus this integral into the input at this instant. This will be the solution of state any time between this to this, including this. Now in this, because we are detecting the outputs at every instance, like delta 1 for output 1, delta 2 for output 2, and so on, delta I for output I, and delta P for output, pth output P. So we are detecting them at these instants, and so the output L delta 1 time, L is, can take these values, integer values from 0 to n1 minus 1. So again, measuring from, this was the time instant k t0, and this is the time instant k plus 1 t0. Now for the, as far as the output is concerned, let us say ith output, we have divided this one in I equal intervals. So this is delta 1, this here it is, from here this is 2 delta 1, 2 delta I, sorry, not delta 1, ith output we are considering. So delta I, 2 delta I, this will become 3 delta I, and so on. As we reach here, this is Ni times delta I. This k plus 1 t0, there is Ni times delta I. So the output after this, L times delta 1, means some time which is L times this, will be given as C1 times X at that time. And C1 is the, means output Y1 we are considering. So C1 is the first row of C. The C matrix is treated as C1, C2, etc. Cp. There are P outputs. So Y1 will be given by this expression. Similarly, Y2 will be given by a similar expression. Only in place of C1 we will have C2. And so on. Ith output Yi will be given by this expression, and so on. Yp will be given by this expression. So all are identical, with the only difference that the outputs are sampled periodic uniformly at the uniform rate of delta 1, delta 2, etc. And in principle, these deltas may be different. Delta 1 may be different than delta 2, and so on. However, they all are characterized by identical equations, and these multipliers are the corresponding row in the output matrix C, as written here. Delta I, as I told, is T0 by Ni, the instant duration, that one sampling duration is divided into Ni equal sampling intervals, that is delta I. Now in place of tau we substitute T0, so we get this one. This is the solution, and in that we substitute tau equal to T0, so we get this one. And what we do is, we from this we solve for xkt0, this one xkt0. We can multiply, pre-multiply all the terms by e power minus at0, and then rearrange the terms. So we'll get xt0 given by this one. So this into e power minus at0 minus this integral and ukt0 pre-multiplied with e power minus at0. And this simplifies, this is as it is. This one, because a t0, this can go inside the integral and combine with this term eat, so it becomes eat minus t0. This is minus at0, this is at, so at minus t0, and we get this one. Now we do a change of variable. We have to basically simplify this part, basically this integral. So we substitute t equal to t minus t0 equal to eta. So t will be d eta. dt and d eta will be identical. However, the limits of integral will change. When t is 0, eta will be minus t0, we see here. And when t is t0, then it will become t0 minus t0, eta will become 0. So limits of integral change and we get this as this. And then we can take the lower side of the lower limit on the upper and the upper limit on the lower, then this can be expressed like this with a minus sign. That can be done. Now we substitute it there. So we get xkt0 equal to, this term is as it is. However, this term, when substituted by this term, this minus makes plus, and then this is that integral. So we get this expression for xkt0. Now next we will do is we will substitute it to in this one. So just go back to see that this xkt0 plus tau was this expression. In that we are substituting xkt0 from here. This one is being substituted here. So we have these two terms, and to that a tau will be multiplying. So it is here, this into these two terms. These two terms up to here. And this term is to be written as it is. So it is here. Now we do manipulations. So this and this, they give this, and this into this term comes inside the integral, and this is as it is. And then further, this is as it is. This one is 0 to tau, and this is 0 to minus t0. So what we have done is, in place of tau plus t, we are making a substitution. So tau plus t equal to mu. And so dt is d mu. However, limits of integral will change like this. When t is 0, then mu will be tau, which is here. And when t is minus t0, then mu will be tau minus t0, which is written here. So this integral becomes in a new variable mu, and it becomes this much. And this one is written as it is over here. So next what we get is, this is as it is here, and we see that this integral goes from 0 to tau. All other things are identical. This goes from tau to tau minus t0. So we have 0 to tau minus t0 here, and rest all the things are identical. So xkt0 plus tau gets expressed in this form. So using that, we will get expression for the outputs y at those fast sampling intervals at the L delta I instance. So because y is c times x, or yi is ci times x, so yi kt0 plus L delta I will be ci times x at that instant, and in that we substitute this expression. So we get yi, this is ci times this plus ci times again this. So we can rearrange the terms, and what we are doing is we are bringing this on the left and we are bringing this output on the right, and of course this will become with the minus sign. So essentially this is going on the left and then we are interchanging the sides. So the state xk plus 1 t0 pre-multiplied by ci e a l delta I minus t0 will be yi at the instant kt0 plus l delta I, somewhere in the between kt0 and k plus 1 t0. So this is somewhere here in between the sampling instants minus this thing which is written here. So now what we do, we obtain such expressions and we write explicitly for each of the outputs. So let me go back. This was Ci like this, ith output. So we write now similar expression for I equal to 1 and of course for various L. So we get C1 e power minus n1 delta 1. Now let us see how this comes. See, this was, if I put I equal to 1, it will become C1 e power a L delta I minus T0. And T0 is how much? T0 is Ni times delta I. So if L is 0, this L delta I becomes 0 and this becomes a T0 with a minus sign. And that T0 substituted Ni delta I, it will become minus a N1 delta 1 for output 1, which is here. At L equal to 1, when L is 1, it will become delta 1 minus T0 and T0 is N1 delta 1. So that will give N1 minus 1 delta 1 into A and so on. So the first term gets like this, e power minus A N1 delta 1 into X at this instant K plus 1 T0. Next one is for L equal to 1, A N1 minus 1 delta 1 and so on for L equal to N1 minus 1 when L was N1 minus 1, then it will give just minus A delta 1. So this is how the left hand side becomes for input 1 for different L. And accordingly we have to now do this. So for I equal to 1 and for different L. So this will give ykt0. How? Because at L equal to 0, this delta 1 will not be there, so it will be kt0. For L equal to 1, it will be kt0 plus delta 1. kt0 plus delta 1 and so on. The last one will be kt0 plus n1 minus 1 delta 1. Similarly, this term. We have to go on substituting different values of L and so we get this one. This N1 delta 1, it comes like this. This was L delta I minus T0. T0 is Ni delta I and L is 0, so Ni delta I with a minus sign. So, and of course I is 1, so N1 delta 1. Next instant it becomes 1 less than N1 and so on. At last it becomes just the delta 1. So we get this for the first output. Now we can have similar expression for the second output. Similar, only in place of C1 we have C2 and in place of N1 we have N2, in place of delta 1 we have delta 2. We can go on doing like this for all the outputs up to P and we can have the expressions. And we can express them in the concise form, vector form like this. Bold C into X K plus 1 T0 equal to bold Y KT0 minus bold gamma U KT0. and this C, Y and this gamma are given here. So we just go back to see how the terms of C come. So we see for this will be C1 into e power minus a n1 delta 1, C1 into e power minus a n1 minus 1 delta 1 and so on, C1 e power minus a delta 1. So this is here. First one is C1 e power minus a n1 delta 1 and last one is C1 e power minus a delta 1. And next few are for C2 and N2 and delta 2. This is corresponding to output 2, this is corresponding to output 1, this is corresponding to the pth output. So we have N1 rows, we have N2 rows and so on, we have NP rows. So this C has the size of N1 plus N2 plus and so on NP, summation Ni into the other size will be decided by this one, which is of size n by n. So it is p by n overall, and this is n1. So it will be summation of n times the n, small n. Similarly, gamma. Go back to C. Let us see that C2. So gamma is these terms. C2 integral between 0 to minus n2 delta 2 e power at b dt. So those kind of terms give gamma. So this is corresponding to output 1. C1 integral between 0 to minus n1 delta 1 e at b dt. Next one will be C1 integral 0 to n1 minus 1 delta 1 e power at b dt and so on. These are the next N2 rows and these are the last NP rows. NP rows, N2 rows, N1 rows. So again this has number of rows are N1 plus N2 and so on up to NP. And then this is Y. Y comes from here if we concentrate. This is Y2 at KT, Y2 at KT plus delta 2 and so on. Y2 at KT plus N2 minus 1 delta 2. So these are for first output, samples of first output taken at KT0, KT0 plus delta 1 and so on. So n samples. Next are N2 samples generated by sampling the second output and so on. Last few are NP samples generated by sampling the pth output. So this is how the Cx equal to y minus gamma u, that relationship is obtained. Here it is written C is n bar by n. N bar is summation of all n1, n2, etc. N is system order. Gamma is n bar by m. M is number of inputs. And y is n bar. So all of them have n bar rows and different columns. C has n columns, gamma has m columns, and y has just one column. This is what I was telling, n bar is summation. So now this is okay, I will come to that, elaborating that equation, what it physically appears as. But we first see interpretation of y. This bold y kt0 is a stack of all multirate sampled outputs during the interval this k plus kt0 to k plus 1 t0, interval of length t0. So n1 samples of y1, n2 samples of y2 and so on is stacked. This is n1 samples of y1, n2 samples of y2 and so on. So this is a stack of samples of y1, y2, etc., yp taken at, of course, at t equal to kt, kt plus delta 1, delta 2, etc., kt plus 2 delta 1, 2 delta 2, etc., and so on. So this is what the stack of output is. And this is what I was telling, that this ykt0, this stack, these samples are expressed in terms of the state at k plus 1 t0 and the input at kt0 state. So this is probably written in the next two bullets, that this expression relates that output stack to the inputs and the final state x k plus 1 t0. This is the expression we wanted to derive, and we have got that. In the previous slide it was told what are the different sizes of all these terms. So there are two more observations. One observation is rank of C will be n, the system order, as long as the n1, n2, etc. are larger than or equal to the observability indices of different outputs. So if the observability index of output 1 is new1, then n1 should be larger than or equal to new1. Observability index of output 2 is new2, so n2 should be selected greater than or equal to new2, and so on. So as long as we do that, this rank of C will be equal to n. That will be ensured. The second thing is that rank of C gamma, capital C gamma, will be n plus m, subject to these conditions. First condition is that AC should make an observable pair, and this augmented system ABC0, its rank should be n plus m. N is the system order, m is number of inputs, and n1, n2, np, etc. are larger than or equal to observability indices of this system. This is the row, ith row of the output. So if these three conditions are ensured, then this C gamma matrix, bold C, bold gamma, it will be of order n plus m. So about this relationship between the system state, output, and the input, we have these observations, that C, by ensuring enough samples, and enough means larger than equal to the observability indices of different outputs, C can be made to have the full rank, and also C gamma, that matrix, can be made to have full rank, n plus m rank and n rank. This can be done. So this is the relation we wanted to derive. We have come to that. Now let us summarize what we have done so far in this part of the video, in this video lecture. So we assumed at the beginning that the sample data control can be implemented for a continuous time system. This is our starting point. The continuous time system can be sampled, and the control can be implemented as a sample data control system or a discrete time control system. So MROC provides a promising option of placing the poles arbitrarily. We are yet to see, we will see. And if that happens, then of course a observer will not be needed. If we recall, in order to implement a state feedback gain which places all the poles of the system arbitrarily, subject to that complex conjugate pole pairs, it was necessary to design an observer to implement the state feedback gain. And if we resort to multi-rate output control, we'll see in the next lecture, observer will be completely obviated. It will not be needed. And of course, to develop the multi-rate output controller, we have obtained this very important relationship, which is this relation. This is the basic mathematical relation which we will be using in the subsequent development. So with that, let us stop, and we will again assemble. We will come across to see the multi-rate output controller. Thank you. See you once again.